In this video, we'll talk about segment relationships in circles, specifically the intersections of chords, secants, and tangents all within a circle. So we're going to go over 3 different theorems and 3 quick examples. In this first example, this is talking about the chord-chord product theorem. And what's happening here is if I have a circle with 2 chords that intersect each other, I can take the segments created by the intersections and I can multiply them together. So I can do AE times EB, and that's equal to, let's get a different color here, AE times EB is equal to CE times ED. Okay, so let's see what that problem looks like when we do general application. In this case, let's do an archaeology application. So archaeologists discovered a fragment of an ancient disk. That's this orange part right here. You can kind of see some hieroglyphs in there. To calculate its original diameter, they drew a chord AB and its perpendicular bisector PQ. Our job is to find the disk's diameter. Okay, so what I'm going to do is I'm going to take this segment right here times this segment, and then I'm going to set that equal to this segment times this segment. Except we don't know this segment over here, so we're going to have to just call it x. Alright, so let's say we've got 3 times x, and that's going to be equal to 5 times, do we know segment QB right here? Let's look up here. Right, okay, because it says it's a perpendicular bisector, that means that both segments are 5. There we go. So now we have 3x equals 25, and when we want to solve for x, we're going to divide by 3 on both sides, and so this gives us x equals 8 1/3. But we need to know the full disk's diameter. Okay, so this is going to be 8 1/3 plus 3, and our answer is 11 1/3 inches. Okay, that's chord-chord product theorem. Next up is secant-secant product theorem. And what's that saying is if I have 2 secants that intersect with a circle, we can multiply, we can do similar work but not quite the same. We can multiply a couple lengths to get, to get relationships formed. One of them specifically is I can go from A to E, so this is that full length, A to E times B to E is going to equal C to E, that full length, times DE. Okay? Well, let's do a little bit of math to see if we can apply this. Find the value of x and the length of each secant segment. Well, what I'm going to do is I'm going to say that this full length, DE, so that's 9 plus 7 is 9 plus 7, that's going to give me 16, times, and then this segment right in here, which is 7, is going to equal GE, so that's going to be x plus 8. Okay, so, well, we'll just leave it as x plus 8 times 8. Okay, we have to do a little bit of distributive property here, so I'm going to get 8x plus 64 because I multiply 8 times 8 and 8 times x equals 16 times 7. Well, 16 times 7 is 112 equals 8x plus 64. Let's subtract 64. Subtract 64. 112 minus 64, and that gives us 48. Okay, things are looking good. 48 equals 8x. Divide by 8 on both sides, and x equals 6. Bam, there we go. Okay, one final theorem to go, and that one is going to include tangents. Okay, so this is the secant-tangent product theorem. And what this is saying is sort of similar to what we used with the secant-secant theorem. I'm going to take this full length, A to C, and I'm going to multiply that by BC, and it turns out that that is equal to this length, DC squared. Okay, so let's apply this here to a problem. Find the value of x when we have this kind of triangle. Alright, well, let's see here. I'm going to do length ML times JL, and that's going to equal length LK squared. Okay, so length ML, that's 5 plus 15, which gives me 20, times just 5. And then on the other side, that equals x squared. Okay, 20 times 5 is going to be 100 equals x squared. So we need to do the square root of both sides to get rid of those. And now x equals 10. Cool. So there's that length.